I'm going to share my screen. I suppose that you can see the slides.
Yes.
If not, please tell me. And okay. So again, hello, good afternoon. Well, first, I hope that you, the DASEE master students, have finished your assignment for today and uploaded to its place in Moodle. I won't accept emails with attached files, so please try to enter the platform, the e-learning platform, and use it. Only Moodle. I will send a new assignment for next Tuesday, and I will also publish, well, it is already published in Moodle, but it is on mute form, so I will make it visible by the end of the class. Before starting, I recommend you re-downloading the slides of this first chapter. So I've made some minor changes, but you may wish to get the last version. This last version, well, you can find it in Moodle. It has a suffix version 2, and I've also uploaded the slides in Microsoft Teams, in the Microsoft Teams area for files. So I suppose that you have them all. So it is more or less where here in files we have session 1, and you know this suffix version 2. It's because I've made some minor changes, and you will also find the presentation for this session, which is the methodological part of an overview of the methodology I will propose you for this session. So, okay. Well, in this second session, we will first go on analyzing the antecedents of the methods I am going to present in this seminar. So there are some antecedents, as you could see the other day. Specifically, for today, we have 3 papers. These 3 papers were written after Serge Rey's contribution and introduced spatial Markov chains as a new tool. The first of these papers was written by your professor and the director of this master's degree, Professor Julie Legallot. It was written in 2004 and published in the International Regional Science Review. The paper was entitled "A Space-Time Analysis of GDP Disparities Among European Regions, a Markov Chains Approach." The purpose of this article is to study the evolution of GDP disparities among a group of European regions, 138, over the period from 1980 to 1995. To this purpose, she applied different methods. First, the exploratory spatiotemporal data analysis, or ESTA, by means of kernel density functions of the main variable. The main variable was relative per capita GDP, and she represented, as you can see in the slide, these kernel distributions for different periods. Second, she also applied the intradistributional mobility analysis of this variable using the method of Markov chains. Third, the spatial Markov chain analysis was also introduced in this paper to quantify the role of spatial dependence in the spatiotemporal process. So the spatiotemporal process takes place because it's a question. We can find some kind of spatial dependence, spatial interaction. So this spatial interaction among the actors of this phenomenon is affecting or not affecting to the evolution. This is the idea. So in this figure, she presented the ESTDA analysis with 2 They are two density functions. These density functions were computed for Europe relative GDP measured in EQs, GDP per capita, for 2 periods. The initial year, 1980, and the final year, 1995. Density plots may be interpreted as the continuous equivalent of a histogram. So it's more or less like a histogram that is continuous, in which, in this histogram, suppose that the number of intervals is set to infinity and then to the continuum. So it is more or less like a histogram. It's not nothing more than a histogram, but a continuous histogram. On the horizontal x-axis for this figure, the value 1, you see here the value 1 in this horizontal axis. So the value 1 indicates the European average GDP, per capita GDP. 2 here indicates twice this average, and so on. In 1995, if we compared this distribution with that of 1980, more regions reported per capita GDP either below the European average. So see the arrow here, okay? Or in this year, in the last year, in 1995, not only this mode we can find, but also we find more regions that reported twice the European average, this value 2. So they are the main differences we can find. Moreover, besides the main mode, a second persistent mode for the time period is situated at around 50% of the EU per capita income. So here, this mode is 50%. So you have this difference, so more regions below the average, and this small or smaller mode, okay? This may reflect the existence of a group of regions. You have here the group of regions with per capita GDP levels well below the average, okay? They are converging towards a lower GDP level compared to the rest of the regions. So it is more or less similar, not so exaggerated, at the twin peaks in the QA paper, if you remember, in the last session. Finally, there is also a small peak, which is situated at around 180% or 200% of the European average on 1995. It possibly is indicating another tendency, but in this case for the very rich regions to diverge at the end of the period. So they converge each other, but diverging from the rest of the European regions. This is the way we could interpret this kernel distribution. So the kernel distributions are not very complicated to compute. They are very simple, like, as I said, continuous histograms. The key issue here is how to interpret them and how to interpret the different shapes. This is the idea, okay? Therefore, we have, or there were, a rising trend to polarization. So from 1980 to 1995, the process, in terms of per capita GDP relative to the average, this process went to a polarization of European regional GDP. There were two significant local clusters. The first one includes regions with per capita GDP below 75% of the EU average, and the second one comprehends the other regions. And additionally, there were also a small exclusive club of prosperous regions above more or less 200% of the EU average. So this is what she found for the European regions at that time. The second method applied to this research was the analysis of the intra-distributional mobility by a 5x5 Markov chain. This table contains the transition probability matrix between 1980 and 1995. These probabilities were estimated by a method, an estimation method. We applied, or she applied, and the people that normally work with this kind of methodology, we applied a maximum likelihood method, estimation method, for the variable, in this case, for per capita GDP. These probabilities are defined as the ratio of Nij over Ni. So Nij, what is that? Is the number of regions moving from class I in year t minus 1 to class j in year t. So it goes from one class to another class of this variable that has been previously discretized, as you remember. So it's a movement, a transition from one class I to another class j. In I, the region was in I in t minus 1, and the transition is considered as one jump in time from t minus 1 to t. And we estimate this number of regions moving from one class to another from t minus 1 to t, period by period, over 15 years. This number, so these 15 years are the years between 1980 to 1995, okay? This number of regions is divided by Ni. Ni is the total sum of regions who have been ever in class I over the 15 years. So in the denominator, we have the total number of, the total sum of regions that have ever been in class I. So it is like the origin over the 15 years. The origin to the destination, the origin is I and the destination is J in terms of classes, okay? For example, during the 15-year period, there were 416 instances, this number, okay, of a region having a per capita GDP in class 1. That is the lower, like 75% of the European average. The majority of these instances, so 95.9%, remained in that GDP class at the end of the year, while only 4.1, this one at the right, percent moved up one class by the end of the year. Okay? So only these two non-zero values. The majority stayed there, and the probability is very high of staying, and only 4.1% moved up, okay? Because it is not possible at this class to move down. So this is why they remain. We don't know to what extent they remained, but well, this is the way we have to compute this analysis. Hence, what we can say of this result is that the poorest regions of the EU experienced high difficulty in scaling to wealthier class in terms of per capita GDP. So a high persistence in this lower class for these regions, even higher than for the others. So highest persistence was found in the lowest class and in the highest one. So in the intermediate classes, we have more jumps, okay? Additionally, Professor Legalu analyzed the ergodic distribution. This ergodic distribution can be interpreted as the long-run equilibrium of regional per capita GDP distribution in the regional system. So this is the ergodic distribution, and it is the long-run equilibrium. These figures, the numbers, must be interpreted as the probability for a region of having a per capita GDP in each of the classes or states for the initial distribution and the ergodic, the long run, in the future, And it is very interesting to look at the differences and even to look at the different amount of these probabilities. Hence, first, concentration of the frequencies in the median class. So in the median class are like more or less here, in 95%, 110. So if we have a concentration of the highest frequencies there in the median class for the ergodic distribution, it would imply convergence to the mean. So maybe we don't have a convergence to the mean because we have that the highest value is here in the lowest class. But if we had these highest values here, we could think that in terms of per capita GDP, the European Unions goes to an average to the mean value, which would be desirable. But concentration of the frequencies in some of the classes, which is a characteristic of a multimodal limit distribution. Suppose that we have the highest distribution, I don't know, that you have them like in the lower class and here in the upper or middle upper class. So it would be, an indication of a multimodal, two modes. This distribution in the long run will have two modes, and we will have a tendency toward a stratification into different convergence clubs. So again, something like the Twin Peaks. But what we have here is more or less this part. Finally, a dispersion of this distribution among all classes, and we more or less have this kind of dispersion. So we cannot find, very, very high value close to the or closer to the median or concentrated in some classes. So they are more or less dispersed. This is the point. So if you have dispersion of this distribution among all classes, we must interpret this outcome as divergence. And this is the situation found by Professor Legalo for the European regions. Divergence in the long run in terms of per capita GDP. So not good news, we could say. As in the analysis for the US regions tackled by Serge Rey, if you remember, Professor Legalo also represented on a map the two types of moves. Moves in the transition probability matrix, moves upwards, moves downwards, and also no moves, stability, okay, immobility. And this is why we have, well, an out of sample is because, in this map, there are some countries that weren't included in the sample. So upwardly move, mobile, downwardly mobile, and stationary, no move, okay? So in this case, what she found was upward moves located more or less close around Germany. Around Germany, we have this upward mobile upward moves, whereas downward moves were mostly found in French and UK regions, more or less. It's not totally clear, but more or less. So this visual conclusion, so it is a conclusion that is visually taken, but this is why it had to be confirmed by a formal spatial autocorrelation test. Specifically, the one that Julie Legalo applied was the Cliff and Oates joint count test. Okay, it's not the normal or the classical Moran-Sai. So many of you, of all of you, should know this Moran-Sai spatial dependence test or spatial autocorrelation test. So in this case, she didn't use this test. In this test, what Professor Legalo wanted to know is to what extent these movements, up, down, or no move, are correlated in space, and to what extent a spatial location is affecting a region to go up or down or not moving at all in the transition probability matrix. This is the idea. But why this weird, maybe for some of you is weird, joint count test? Well, it is not very weird. It was proposed by Cliff and Oates, I think that in 1975 or 78. They have two very important books during the 70s, Cliff and Ord, and it was reported by Luc Anselin since very, very early in his first software, SpaceStat. So it is not so weird. The point is that it is not very, very used. The joint count test is the appropriate test to detect a spatial autocorrelation when we are working with count data. Count data. Why count data? Because we have three values. We have upwardly mobile is one value, downwardly mobile another value, and stationary a third value. So this variable, weird variable, but variable that we are representing on a map, takes three values, two for upwards and move and downwards transitions, and another one for immobility. This is why if you want to compute for this kind of variable spatial autocorrelation test, you should use the joint count test. For the ones that know Geoda introduced this test. I can remember. I think that in the last versions it is there. We will see because I will present briefly Geoda just to let you know. And this specification needs to know which are my neighbors. So if I want to see if neighboring regions is affecting one region in terms of these movements up and down, I need to define neighborhood, a spatial neighborhood, okay? The specification that was used by Julie Legallo considered as neighbors those regions located in a radius of a cutoff distance of exactly 321 miles. Why this concrete threshold? It is because it was the first quantile of the distribution of distances among regions in the EU. So if you compute all the distances among this sample of European regions, you find that the first quantile of this distribution of distances was 321. It's a way of defining a neighborhood when you don't have, an exact knowledge of which should be the neighborhood criterion. This is the idea. So you can opt to use different ways of computing, or even to make a kind of robustness test with different ways of computing this spatial weights matrix. But this is one of these ideas, taking into account just the distances among the regions of the elements, the observations of this sample. The non-zero elements of the spatial weight matrix are calculated as the inverse of the squared distance. So many times what you do is, if you are my neighbor, I assign you a 1. And if you are not, I assign you a 0. Well, in this kind, these ones have been refined in terms of this distance among regions, okay? So in fact, the exact measure is like a gravity model, is the inverse of the squared distance between the two regions located inside this cutoff distance. And outside the cutoff distance, I assign a 0. So no neighbors at all. So we are not neighbors because it is considered as a very large cutoff distance. Even as you can see in the slide, Professor Legallo tried with some other radius, broader ones, considering not only the lower quartile, but the median or the upper quartile, to see if she had a robustness. So she found autocorrelation also for different radius of neighborhood. And of course, she did. So this was the main outcome. And finally, she also used the spatial Markov chains. If you remember, we define a different, so the spatial Markov chain, in this case, is the more complete one. So I have a different transition probability matrix for each of the spatial lags. So depending or conditional to the class where the spatial lags, the spatial neighbors, are the class in terms of per capita GDP. So in this case, I build the probability matrix from 1 to 1 to 2 to 3, etc., for all these regions that have neighbors in the lower class. So to see if being or having neighbors, we could say having bad neighbors or poor neighbors, if this situation is affecting or not to the probability. So it's a very finer analysis. And what she found in general terms is that the richest regions are negatively affected when poorer regions are around them. Is one of the of the outcomes. For example, regions in class 1 will jump to class 2 with a probability of 5.9% if they have neighbors in class 2. So they are in 1, but since they have neighbors in 2, they have a probability of more or less 6% of jumping up to class 2. This is the way we should interpret these results. While regions in class 5 will fall to class 4 with a probability, a little bit higher probability of 9.2, more or less, or 9.1%, if their neighbors are in class 4. So if I am in class 5, but I have neighbors poorer than me, the probability of going down with them is 9.2%. Okay? Well, in 2008, Professor Julie Legalo and I published a new paper with an application of this methodology. It was published in Empirical Economics with this title, Spatial Analysis of Urban Growth in Spain, 1900 to 2001. We studied the evolution of population. In this case, what we wanted to do is analyze the population growth over the period 1900 to 2001. So over the period of 10 decades, more or less the whole 20th century, okay? Among a group of 722 municipalities, there were cities and towns, which are actually part of the Spanish urban areas. So in the Spanish urban areas, we find 722 cities and towns, and we wanted to see which of these actually urban areas, locations, could be considered as winners or losers in terms of size, if they have experienced an increase in size, in volume, during this long process of 100 years, or the contrary, if they have lost population. In fact, we are now talking about the empty Spain, so the Spain that is becoming empty, desertified, because people are moving massively to these urban areas. And it is a problem for these small villages with very, very few people and not very well attended in terms of services. Well, this is a big problem in our country now and in other European countries. We applied different methods to do that. Well, first, the exploratory spatiotemporal data analysis, in this case on the main variable, population. Second, an analysis of the intra-distributional mobility of this variable with the method of Markov chains. And third, the analysis of the role of spatial dependence in the intra-distributional mobility of population. So if this mobility, intra-distributional mobility, was affected or not by the vicinity with determined cities, or the determined sizes of these cities, spatial dependence. In this slide, what we are representing is the population distributions for different key periods in the Spanish history during the 20th century. Well, periods interesting in terms of population: 1900, 1950, 1970, and 201. So in 1900 is it's the beginning of the 20th century. In 1950, we were experiencing a very crude situation after our Civil War and the Second World War, and we were isolated, and the situation was really complex. Many people had to escape from cities to villages because they had lots of needs in the cities. 1970 is a complete different time in our country. Cities started to grow massively in very, very big cities or very big agglomerations. And in 2001, the situation reverted because urban sprawl. So they were, in fact, interesting points in our country during the 20th century. The variable was, of course, transformed in natural logarithms, but relative to the log of the population average of this group, the group of municipalities that are actually present in the urban areas. So we could say more or less they are urban municipalities, so big cities and towns, most of them. So we are not going to find villages. Hence, here, the value of 1, you can see here the value of 1 in the x-axis, represents the population average of the Spanish urban municipalities. Okay? So, if we look at the 1900, the distribution is bimodal. Bimodal, clearly bimodal. You have two modes, one more or less, yes, above the average, and the other, but very close to the average, but bimodal. But in 2001, the distribution experienced a shift, as you can see, a shift up. So it is very interesting because it becomes more or less unimodal, though it still keeps a minor mode around 70, more like here, 70, 80% of the national average. But this progressive concentration of probability mass around 100%, around this one, how can we interpret it? Well, it is a sign of convergence in population size of the urban municipalities. It could be understood as logical, since these municipalities are nowadays the main towns and city areas in Spain, while 100 years ago, they could have been very different in size. But this is what we found. Again, the Markov chains, the intradistributional mobility was analyzed with a 6x6 Markov chain, in this case, six classes. For example, if we consider the lower class, where there were 2,567 instances. They are instances of an urban municipality having a population size lower than 20% of the Spanish average. So what we find here is the number of observations or instances that one of these municipalities had this size that was lower than 20% of the Spanish average. The majority in this first row, the majority of these municipalities, 24.4%, like in the other case, for per capita GDP in the European regions, that here the same. This remained in that size class, so higher, very high persistence at the end of the year, so from one year to another, while 5.3% moved up one class by the end of the year, and well, only 0.2% moved two classes from 1 to 3. So it's not so easy for a municipality to grow. In this case, it is not a year. It is not from 1 year to another year. It's from one decade to the next decade, 10 years, okay? Because they are data coming from the census, and our census are made by each 10 years, okay? The ergodic distribution, again, was computed. And as in the previous case, it must be interpreted as the long-run equilibrium of the urban size distribution in the urban system. So where are our urban municipalities going in the future? Where are they going? Well, in this case, we see that with this red square, highest values are concentrated in the first classes. So the way we should interpret these values is that there will be a time where the distribution of urban municipalities will not change anymore. They will remain stacked. And this is the ergodic or the limit distribution. So the time of complete immobility, so they reach their trip and they stop. This is the idea. The ergodic distribution is interesting because it is used to assess a form of convergence. As we said before, concentration of the frequencies in certain classes, in this case, would imply convergence to this class. So in this case, convergence to the first and second classes, because it is 0.2, 0.3, and considering not only the initial, but the ergodic. So there's not a lot of difference between them. In the middle class, if the concentration is in this middle class, it will be convergence to the mean, as I said. And as we can see here in the Spanish urban system, the higher frequencies correspond to the lower classes. And this points out to a convergence to these small size towns. So we are going to a convergence to smaller size towns. So the big cities are going to spill over to the metropolitan areas and the peri-urban areas, peri-urban areas. If concentration of the frequencies are in some of the classes, this is not the case, but it could be, it will be interpreted like a stratification into different convergence clubs of cities. This is not the case in this set of cities. And if we had this no special concentration, it would indicate divergence. So finally, what we did is computing a spatial Markov chain matrix, but in a different fashion, as you can see. We only contemplate three movements, going down, going up, or staying in the same class, these very simple movements, and we take into account the spatial lag of each municipalities, in the sense that they could have less population or being in a lower class state, being in the same class, or having more population because they are in a highest population class. So it is more simpler than the very big matrix of matrices that we saw in the case of Julie Legalot's paper on GDP. In this case, less means that the spatial neighbors of a locality are in average in a lower class, as I said, okay? And more that they are in a higher class. So if a probability of a particular transition of going down, none, or up is conditioned on the populations of the urban municipalities' neighbors at the beginning of the year, this would be because there is some degree of spatial autocorrelation. This is the idea we are looking for, okay? For example, in Spain, the probability for an urban municipality of moving up in the hierarchy is 7.1. 7.1, when its spatial lag contains on average less population. So the probability of going up, getting more population for an urban area municipality is 7.1 if they have less population, and 8% when it contains, on average, the spatial lag of the surrounding municipalities contains, on average, more population. So we see that, there is a kind of connection. Conversely, the probability of moving down when its spatial lag contains, on average, less population is 18.9%. So it is higher. So the effect of having less population around for a municipality, the effect for this municipality to also go down in the distribution is highest than the effect of to go up. Okay, in this case it could be normal, but here, for instance, also 8% versus 19.1%. So it is curious the the strength that movements down has, or we get these higher figures for these movements, downwards movements. Of course, to stay in the same class because of the persistence is normal. It is not so easy for the population to move in this relative distribution. So it is relative to the average. Of course, that people are growing in Spain and everywhere, but we are taking into account the relative movements in the distribution. So if they go up, they all go up. But we are taking into account the distance to the median of the whole distribution, for instance. This is what we are doing. And okay, so the next paper was written by Agovino. Agovino, this Italian researcher, published this paper in Annals of Regional Science in 2014. It was entitled, "Do Good Neighbors Enhance Regional Performances in Including Disabled People in the Labor Market? A Spatial Markov Chain Approach." So it is interesting because it is one of the antecedents, or the first ones, that take into account social analysis. So it's socio-economic, but more social. In this case, it is the ability of regions, the regional governments or regional companies, to include disabled people in the labor market, to employ them. Okay. So the purpose of this study was to examine whether the performance of Italian regions in providing employment to disabled people can be affected by the performance of neighboring regions. So I have a neighbor that is doing very well in these terms, maybe this will affect me because we have this vicinity. And maybe the regional governments are going to compete, and in the end, being closer in terms of geography, it could be important or significant in this phenomenon. The results of this analysis showed that good neighbors were important in promoting employment to the disabled. However, the effects produced by bad neighbors should not be underestimated, especially when show time-space persistence. So again, the bad side seems that be winning to the bright side. But well, let's see. This is what they found for Italy. Well, they use a different variable. So first, we are talking about GDP per capita, population. Now they use the percentage of employed disabled people. They applied all the analysis to these percentages. They computed this variable for the 20 Italian regions from 2000 to 2009. Finally, the last paper presented in this antecedents chapter was written again by Agovino and two colleagues, Crociata and Sacco, in 2016. And it was entitled "Location Matters for Pro-Environmental Behavior, a Spatial Markov Chain Approach to Proximity Effects in Differentiated Waste Collection." It was published in Annals of Regional Science. Again, it's a phenomenon that has to do with behavior, good behavior, good way of doing things. In the other case, it was, giving jobs to the disabled, and here is having a pro-environmental behavior expressed as a ratio, the differentiated waste collection. Well, the authors analyzed data on a ratio. This ratio was the differentiated waste collection. This ratio is presented here. This is a curious way of quantifying this measure. And this measure is a proxy of what we could call pro-environmental behaviors in general. These data corresponded to the 20 Italian provinces in the year 1999 to 2012. They made use of a spatial Markov chain approach to model the dynamic environmental pro-sociality to study if waste collecting habits tend to be influenced by proximity effects. In fact, what they found was that provinces, Italian provinces, with good levels of environmental pro-sociality may positively influence nearby ones and vice versa. So provinces that are doing bad also influence the nearby provinces. So it is a kind of positive spatial autocorrelation because high produce high around and low produced low around. Okay. Well, in order to construct the spatial Markov chain, they defined 5 states of the variable. The variable is the differentiated waste collection rate. It is a rate with respect to the country mean, always relative to the country mean. Don't forget that we are computing variables. We want to measure the evolution of variables in relative terms. So they should be always relativized or, divided by the country mean. These states were defined as poor, lacking, average, fair, and good pro-environmental behavior or pro-sociality based on different powers of the standard deviation from the mean. This is another way of computing this Markov chain. So the way of discretizing, how discretize this variable, that is a rate, in order to call to the classes poor, lacking, average. So a way of doing that is subtracting or adding the mean different standard deviations, 1 standard deviation, 2 standard deviations, 3 standard deviations. And as it can be seen in the outcomes, good neighbors at the beginning of a period improve performance of a province in the next period. That is what they wanted to find. And also with the bad. But a good thing is that if we promote, with social policy, we promote good behavior in terms of environmental issues, it is going to have an effect not only in a province but in nearby provinces, which is very interesting because it's something that is more or less like natural because of interaction among people, because they live in one province but maybe they work in the other one, or they have relatives or friends, whatever. This kind of interaction are doing this effect that something that you are preparing or you are establishing in a region can affect nearby ones. Okay, so this is the end for this first chapter. Well, the aim of this first chapter was showing you the antecedents and putting you to start studying more in depth all these methods and some new ones, as I will show you. Sorry. So let's go to chapter 2. You can find chapter 2 in Teams and also in Moodle, of course. You can download it. Let's see where it is. Let's see. Chapter 2, methodology. Okay. So let's go to the methodology. Well, after this first chapter on antecedents, we will get into the presentation of some tools these 1, 2, 3 to 6 tools that constitute a specific methodology. They could constitute a specific methodology prepared to analyze intradistributional changes of a spatial sample during a time span. So this methodology is a general methodology for any kind of a spatiotemporal variable or process. Of course, they could be economic processes or variables, but also social ones, environmental, physical ones, etc. This method, this set of tools, will allow us also to detect convergence or divergence of a group of spatial units in the long run in terms of this variable we are analyzing. As I said, it could be any kind of variable. Okay, so the point is that I will concentrate in population because I will concentrate in the paper where we present the methodology. But of course, you can apply, as you could see in Agovino's papers, you can apply any other kind of indicator that could be proxy for something or whatever. Okay. So it is a model strategy. A model strategy to what? To identify spatiotemporal patterns in the evolution of a variable. So we can identify spatiotemporal patterns, patterns in space and time, and also the interactions, the spatiotemporal interactions in space-time. The method also allows evaluating the influence of spatial proximity. So not only how they are spatially located, the variable, as we normally do with different maps, but also the influence of spatial proximity among spatial units, because we can detect regional differences and interactions in their spatiotemporal dynamics. So spatial units, spatial vicinity of units matter and can affect, and they are indeed affecting, the spatiotemporal dynamics. So it's not the same having good neighbors that having bad neighbors in a very simple way, you know. We can analyze different type of spatial units, of course. You will have to look for a database. It is the second assignment. And which kind of database? You should look for a phenomenon that interests you and for which you have spatiotemporal data. But what kind of spatial data? You can, apply this methodology to cities, census tracts, regions, countries, whatever kind of spatial data analysis. With this methodology, we can measure the influence of spatial proximity with a set of 6 statistical approaches. So these 6 approaches we have here represented on this chart. They are approaches to contemplate this spatiotemporal analysis from different points of views. Okay. For this analysis, I will present this paper. This paper was written by Andrés Vallone and I last year. It was published last year in the Annals of Regional Science. And what we are doing here is analyzing the evolution of the Chilean urban system during the 20th century. It was because Andrés lives in Chile, and he was highly interested in the Chilean urban system, which is very peculiar. It is a paper that is entitled Spatiotemporal Methods for Analysis of Urban System Dynamics and Application to Chile. What we do is using the SDAR package. The SDAR package was built in R. You can find it in the GitHub webpage of Andrés. So this is the webpage of Andrés Vallone. And this package was partly prepared in Dijon, like 2 or 3 years ago, I can't remember, with Professor Legalo and one of her students, Kasum Ayuba, and finally, well, he could finish and publish some papers. There is also another paper that was published with them, with Julie Legalo and Kasum Ayuba. But this paper was in a different topic. So what I'm going to present is the paper I know better. That is the one that we published together. Okay, and let's see. Where are we? Okay. For certain illustrations and analysis, I also will use Geoda software. But Geoda software is it's a very easy. I don't know if you know it. It is interesting also for spatiotemporal analysis, and you will find a manual, a workbook in this web page. It is the web page for the Geoda software. Here in the documentation, you will find the workbook. There is a part that is devoted to space-time exploration, but we also will take a look to another operations, GIS operations, which could be very interesting, even to represent spatial variables, not only for spatial temporal analysis, but for pure spatial analysis. Okay, so it is important because for next day you must download this software. It would be very interesting if you downloaded the software and can do some exercises, practical exercises with your own database. So you must look for a database and you must download this software. Here in the download button, you can download it for Windows, for Mac, for Linux, these three platforms. You will find Geoda for different languages, also for Spanish, but I recommend to use the English version in order to have all the same version. It's a pity because I am the author for the Spanish translation, but okay, I prefer you to use English since we will have the same view. Okay. So please come with Geoda installed in your laptops if you want to reproduce the analysis with your own data. I also will give you some proof data if you wish, if you don't have prepared your database, but it would be desirable to have prepared your database. And of course, something that I would ask you to do is to install RStudio. Okay. You please look for the last version of RStudio, and I will send you an email with all these instructions. So don't worry, but I am just advancing them. Okay. Well, and this is the methodological procedure we proposed in this paper. First, exploratory analysis as ever. We analyzed with this exploratory analysis convergence and divergence in the spatial urban analysis and even urban regimes, spatial regimes, with the sigma convergence, the kernel functions. Again, the intra-distributional mobility analysis, the classical one with Markov chains, and the analysis of spatial effects. Spatial effects in the broad sense, as spatial autocorrelation and as spatial heterogeneity. Spatial autocorrelation effects can be measured with the spatial Markov chains, but also with the LISA Markov chains. The LISA Markov chains allows us to analyze the coevolution of cities. But if we have identified different spatial regimes, spatial groups of, in this case, of Chilean cities or of provinces or of municipalities, of whatever spatial units, if we have identified these regimes, we can also analyze a kind of coevolution among the regimes with the GMA index, and the cohesion existent among the spatial regimes with the rank decomposition index. I will show you these points, okay? Each of the items. Well, the spatial Markov chain, as shown in the antecedent chapter, has been used to analyze the historical development of Spanish urban cities and towns, as it was my case. But not only for Spain, it has been applied to some other urban systems. For instance, you can find an interesting paper written for Phoenix, Arizona. But it is not easy to find similar analysis with spatial Markov chains applied to other spatial systems on population. So I'm saying that because maybe you are interested in urban systems. So perhaps you can take data for your own country, for France, or for any other countries, and try to do something similar to what we did for Spain, Julie and I, or for we have done, Andres and me and I, for Chile, okay? And so this is, something that I recommend. So we have this procedure, this six-step method, as I told you, and we go now one by one. Okay. First, exploratory analysis or exploratory spatiotemporal analysis. The typical spatiotemporal exploratory analysis, you have some of these analysis in Geoda, for instance. Okay? This typical analysis does not allow you to analyze the evolution of the shape of the cross-sectional distribution of cities. So if you want to see the shape, you need the kernels. So the shape of this distribution when it is relative to the rest. So this is why it is important to compute the kernel graphs, because we can, measure phenomena like urban convergence or divergence. If we use, for instance, the mean value or the dispersion with the Gini index or sigma convergence, so they are not, of course, bad measures. They have been broadly used in the analysis of convergence and divergence, but they are not enough, because we cannot see with this sigma convergence evolution in time, we cannot see the dynamics of the whole shape, as I said. So this is why we need to look at the complete, the overall population distribution, in this case, distribution of population. We need the kernels. So it is something that is interesting. And compute the kernels, fixing a median, this one, or the average, and putting all the charts one on the other, just to see more, in a more clear way, the evolution of the shapes. This is what we do normally with the kernels distribution. Okay, and what about the distributional mobility, the Markov chains, the classical Markov chains? Why they are important? They are necessary. If we have the kernel density functions, we can see if we have convergence, divergence. Okay, it is true. Of course, they can characterize the evolution of the global population distribution, but they do not provide information about the movements of the cities within the population distribution. So the matrix is finer. It's a finer analysis because you can see the specific movements from one class to another class over the course of the study period. So, for instance, the kernel distributions cannot say whether the right tail of the initial year distribution contains the same cities as the right tail in the final year distribution. I want to see if what is happening in the initial year or in the initial point of time remains, is persistent in the final point of time. And this is what we can do with Markov chains. This is what the classical Markov chains are adding to the kernels. So, because if I don't say so, maybe some of you are thinking, why so many statistics? They look like redundant. No, they are not redundant. They are putting a specific, characteristic. They are highlighting a specific point that cannot be highlighted by the others. This is the interesting thing of this methodology that allows you to contemplate this spatiotemporal analysis from different points of view. And each of these methods shows a different light. Okay? As I said, we can answer all these questions, being at the right tail in the initial year, if they also will be in the right tail at the end. The only way of doing that is with the transition probability matrices that are associated with Markov chains. So as I said, and you are looking in the different analyses, a Markov chain matrix, is a set of discrete states. So something that we will talk about in future sessions is how discretizing a continuous variable. How? We have seen some examples with a 4.4 matrix, 5 by 5, 6 by 5, 6 by 6, but we didn't see, for instance, a 1 by 1. This is stupid. 1 by 1 cannot allow you, but why not a 2 by 2? Or why not a 20 by 20 states? So this is something that we should answer in the following sessions. And but this is very, very interesting. So the Markov chain shed this light, the movements from one state to other states, from one point of time to the following point of time, the next point of time. The third step consists of the computation of the effect of a spatial dependence. Well, in fact, from third to sixth, we have the analysis of spatial effects. In this case, this third step takes into account spatial dependence. Spatial dependence where? On the intradistributional dynamics, on this upwards, downwards, or non-movement in the matrix. Is spatial dependence relevant? This is what we are asking. In effect, population growth, if we take into account population, may spread around neighboring areas. For instance, in a kind of metropolization process, or perhaps it may experience a chronic depopulation evolution, this empty Spain I was referring to previously. These two situations, metropolization and depopulation, correspond to positive spatial autocorrelation. So it's high with high, low with low. Okay? On its part, what negative spatial autocorrelation implies? So is it possible to find negative spatial autocorrelation? Well, it would be a systematic dispersed polarization of large cities in a country, very large cities surrounded by desertified areas. Okay? This is a different way of looking at urban areas or the urban systems or population system in a country. What do we have? This is the idea. Markov chain analysis enables integration of a spatial dependence of the data by estimating the spatial Markov transition matrix. The spatial Markov transition matrix computes, as we saw previously, the probability of a particular transition in a period conditioned by the population of the city's neighbors in the preceding period. So in the preceding period, I am surrounded by very large cities, very big ones. They are metropolis. So the probability that my city grow in the next period will be very high or not. It depends on the degree of spatial autocorrelation. The fourth step, adds what we call the co-evolution of the cities. So we can see how the cities and their corresponding spatial neighbors are co-evolving, evolving together. So what we do is looking at the LISA. If you remember, LISA means Local Indicator of Spatial Autocorrelation. So the LISA is a way of looking in depth the spatial, the Moran's scatter plot. So they are the most significant values at the extreme of the quadrants, more or less. Okay, we will use for this coevolution two methods: the LISA Markov chains and the directional LISA. They are two ways, to compute and to visualize the results. So these LISA Markov chain and directional LISAs are giving something new. They can give you the information about the joint evolution of cities and neighbors. So it's a way of moving up and down, in the transition matrix, and if they go together or not. The LISA transition matrix can be also called LISA Markov chain matrix, and it is based on the local Moran statistic. It computes the joint transition of a city and its neighbors in the distribution by measuring their movements across the 4 quadrants of the Moran scatter plot. So, for instance, if a city is at the beginning of the period in the first quadrant of this scatter plot because the values, the population is higher than the average, and it is surrounded by cities that have also, in average, a population over the average, this first quadrant, let's see what happens in the next period. Maybe the city goes to the second quadrant, or it goes to the third one, or it goes to the fourth one, or perhaps most frequently, it will remain in the first quadrant. This is what we are going to do. The LISA Markov method then computes the probability that cities and the spatial neighbors will move, but from the Moran scatterplot states. Each quadrant is going to be a state. High, high, low, 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 high, high, low. They are the new states, being in one of these scatterplots. And what is the directional LISA? Well, it is necessary because sometimes it is not possible to observe in a direct way this coevolution. So it's a kind of graph. You can graphically represent the co-movements. And this is what we call the directional LISA approach. Okay. And what about the last steps, the fifth and sixth step? Well, they are devoted to the analysis of the influence of the other spatial effect, spatial heterogeneity. Well, sometimes we have in the spatial system, among regions, among provinces, in Europe, wherever, in the United States and whatever other country, we have what we call spatial regimes, spatial groups of regions or parts of the country or wherever. In this fifth step, what we do is computing the global index of mobility association, the GIMA. What is the GIMA? The GIMA is based on the rank correlation coefficient. It enables measurements of disparities or inequalities in city size, for example, using concordance or discordance of the ranks of this variable into periods of time. So if I rank, the cities from the largest one, Santiago in Chile, to the smallest one, I don't know. And I do the same with, the in one period, and I do the same with the other period, I can compute the rank correlation coefficient and see if I find disparities or inequalities. So the GMA is a spatial tau index of concordant and discordant rank pairs, which can capture the effect of space in the ranking changes. This is the GMA. What we do is compute the ranking for different moments in time, and the spatial tau will do that for space, considering specifically space, and see if the ranking changes from one year to another year, from one decade to the following decade, if these changes in rankings are due to spatial effects. Okay. In turn, the GMA can be decomposed into two indexes, one for pairs of neighboring cities and the other for pairs of non-neighboring cities. We do that in order to identify the different rank correlation patterns. If we have rank correlation patterns that are different, if we consider pairs of neighboring cities or pairs of non-neighboring cities. And we will get the flavor of what is going on with these changes in rankings. Additionally, it is possible to partition the cities into regimes by computing the spatial neighbors with the so-called block spatial weights. I will show you what is a block spatial weight. So considering different regimes in the urban system. And finally, the rank decomposition index is defined as the sum of rank changes from a first period to the following, and this within a spatial regime. And we contemplate the sum of these rank changes within a spatial regime, considering over the total of the overall rank changes. So we see if the changes in rankings within a determined spatial regime is different or not over the sum of the overall rank changes. For a sequence of time periods, this index will measure to what extent the rank changes of a variable, which is measured over n locations, are in the same direction within some spatial regimes on the n location. It is necessary, in this case, that the spatial regimes are mutually exclusive and exhaustive partitions. So we must divide exactly the complete set of the sample in regimes. So I cannot leave cities or observations out of the regimes. So I must split the whole sample in mutually exclusive and exhaustive partitions of the n locations. So what cohesion means in this context? Cohesion can be understood as a process of migration between regimes, such as the size of cities in one regime increases, ascending in the ranking, at the expense of the size of cities in the other regimes, which decline in the ranking. So it's like a communicating vessel. So I grow, this regime grows because it is at the expense of the other regime. Therefore, in this context, the full cohesion implies a perfect population transfer, or whatever transfer, between the spatial regimes. And this is what we can measure with this rank decomposition index. And well, that's it for today. Now, please, let's go to the assignment I need you to prepare for the following session, okay? The following session will be next Tuesday. You will find this instruction file in Moodle. This is for the DASEE master students. Okay, and this assignment consists in the construction of a spatiotemporal database. So if it is not easy for you, maybe, I don't know, to build this database for Tuesday, you will have more time to do that, but not a lot. I recommend you to prepare your database as soon as possible, because your final assignment, the most important one, that will be the presentation of your topic, of your analysis will consist of what we are going to do in these classes. So we are preparing the assignment through the classes. So this is why it is important to build your own spatiotemporal database as soon as possible. If you cannot, for next Tuesday, well, don't panic. I will give you a database to play with it, but it is not going to be your own database, of course. And well, you must look for a panel. So you are looking for a panel database. Choose an interesting topic. It could be income, population, quality of life, crime, employment, environmental issues, social issues, population, whatever. They must take into account the following restrictions. So please, for time periods, look at least 15 years. Don't ask if you can for 14 years, but more or less 15, okay, but not 10 or 5. It is not a lot. So you need, a sample, a minimum sample for the time periods. And for spatial observations, at the very, very least, 20 to 30. I will see 30 or even 50 units. So regions, sub-regions, cities, okay? It is not necessary to have thousands of them. You can, of course. In my case, I was working with Julie Legalo with 733 municipalities, so why not? But it would be enough for 20 to 30, at least for this exercise we are going to do in these sessions. You will also need a map, if you can, a shape map. Okay, of course, for the spatial observation. So if I'm working with provinces, Spanish provinces, or French regions, or whatever, you need the map. Well, for the map, I will recommend you, if you're working with a spatial polygon data, I recommend you to look for the shapefiles provided by official statistics offices, because they are going to be the best ones. For example, the INSEE for France. You can also download administrative regions for any country in the world in the DIVA GIS webpage. For example, here you can download data by country. If you download data for, France, for France, French data. Okay, France. You can download different kind of subjects, but I recommend you the administrative areas, because these are the ones that you are going to represent. If I press on OK and download, I will download this data, and you will see that in this web page they provide you with some maps. So each map shapefile is based on minimally a DBF file, which is the database. PRJ is the file for the projections, which is important. The SHP is for the map, for the representation of the polygons in this case. And this last one, the SHX, is the one for connect the database with the shapefile. And of course, you can have some others, but these are the most important ones. Okay, and you have the administrative 0, 1, 2. So if I open the DBF, for instance, in Excel, I can ask the Excel file to open. You will see only one observation, because it's going to be the map for the whole France, only the country. So you will have only one polygon. Be careful with these DBFs, because you shouldn't, open them. Let's see where we are. Here. Now, administrative 1. They are the regions, the big regions in France. Okay, the 22 regions. If I press and open number 2, they will be the departments. I think, oh, sorry, it's a CBF. It is better the DBF. I think that they are the departments. Okay, well, I'm not sure. It's a kind of, yes, the department, a kind of provinces. In France, you have 96 departments, and well, you can go down, and you will reach to the commune, the communes in France. You can choose which level, which spatial level. Well, it depends on your data. If your data is available for only the department or the communes, and you want to use this very, very big database. So the last one for France is like 33,000 observations. So maybe you are not going to find easily, a database, a spatiotemporal database for this number 5, okay? But this is a good web page. The problem is that sometimes these divisions are not updated. In some countries, the divisions are updated, like it happened some years ago in Peru. I think in Peru, I was working with a database for Peru, and I found out that it wasn't updated here in Dijon. So be careful, because sometimes you won't have an exact match from the map to the database and vice versa. And you have other web pages like the USGS. You can press and go here. The USGS. You will have a database and also a maps. So it's a maps with databases that can be of help for you. And here, this is another interesting web page of the NYU, New York University, with Geographic Information Systems, Spatial Data Repository, and Resources. You will find thousands of these web pages. These are the main ones, as far as I know, and also in Geoda, in the web page of Luc Anselen, you will find some other examples and sample maps and sample exercises. So it won't be complicated, okay, to find this panel database. The point is that I recommend you to arrange the database in this way. So in rows, the regions, as they are, in the maps. In columns, the different variables considering the different periods of time. So this is the variable for period 1, the first. Variable for period 2, for period 3 and 4, okay? This is the way. So please don't pull the data, at least for the moment, okay? They must be spatial based. And some recommendations: please avoid the islands. Sometimes you will find islands, at least in France. I had a student in Spain that came from La Réunion, so very, very far island from France. So you have these lots of islands that they are complicated to deal with. So if you can avoid the islands, it is not easy. If you find islands and you want to eliminate, you must just use GIS. If you can't use it, please ask me and I can help you. Write an email and saying that you cannot eliminate them. But with GIS, it is not complicated at all. And also, don't send me emails. I will show you in Geoda. You can do that in Geoda now. With the last versions of Geoda, you can avoid the islands and get only with the continents. Well, consider that time series should be homogeneous. Homogeneous in the sense that you must avoid methodological or any kind of breaks. So you must have a complete panel, a spatiotemporal panel. I recommend you to use spatial polygon data, but you can also use spatial point data. So in my case, for the municipalities, they were point data, okay? For the point data, you will only need the coordinates to represent this data. If you have the coordinates, with Yoda, you can represent your data very, very easily and transform a spreadsheet into a map, okay? And well, I think that's it. Just please asking the students, the DASEE students, to fill in here in Moodle. If you enter Moodle, just a few seconds, but I appreciate, and I will give you extra points. If you feel, oh, sorry, I will highlight this, the idea assignment show. You can see this, and this assignment will be opened until next Tuesday at 2. And if you need more time, please tell me and I will reopen to allow you to upload afterwards. So during the next week, please don't take a lot of time for that. And please go to this feedback. This feedback is interesting for me. If you answer the questions, not all of you answered the questions last day, so please answer the questions about what concepts have been clarified and what concepts need more explanation. For me, it's very important, and this is why I will give you extra points for doing that. And that's it. Thank you so much for attending the class. And
Professor, may I ask you please a question?
Yes.
Can we use the database which is available on Geoda website? Can we just download it and work with it?
Yes, of course. You can work with whichever database.
So this database is enough to do the analysis?
Yes. The point is that you need a panel. But this is my the panel, a panel that is complete, and you need the map. So if you have everything set up, okay, you can use it. It would be more interesting if you fight with the data, but it is not necessary for my class. So if you find everything together, the map and the time series and all the panel, but the point is that you shouldn't choose the same database. So if some of you coincide, you must change. This is the point.
I have panel data, but I don't have coordinates, location. I analyze countries, like 50 countries or over 40 years, but I don't have coordinates. So does it mean I can search on the internet the coordinates for that countries?
Well, maybe it is not so complicated if you have a country map, a map of countries. But the point here, when you are working with countries, is please be careful. These countries should be connected. So I won't allow to have isolated units, because sometimes you have, I don't know, data for India, but not for Thailand or whatever country. So you need all the whole world, or the countries for one continent, but all the countries, or they are joined in space. This is very important for spatial autocorrelation and spatial regimes analysis.
So basically, they have to be like neighbors, close neighbors.
Of course, yes, to share a common border.
Oh, okay.
Or
thank you very much.
At least not to be very isolated. Okay.
Yeah, thank you very much.
Well, see you on Tuesday. Have a good weekend. Okay. You can see me.
Thank you. Bye.
So, bye. See you on Tuesday.
Bye.
Bye.